Hello everyone, I'm Cheng. I'm grateful to introduce my co-authors, Mr. James Goldschmidt, Mr. Shen, and our advisor, Dr. Lawrence Ukeiley and Dr. Stephen Miller. We come from University of Florida Department of Mechanical and Aerospace Engineering. Today's topic is analysis of acoustic radiation from instability wave within an off-design supersonic jet flow using combined theory and Large-Eddy simulation. We are grateful for continuous funding from SEDEP and the Office of Naval Research. The outline includes introduction and background methodology, including the combination of theory, experiment, and numerical method. The results analysis, including flow field, acoustic, and statistical analysis. Finally is a summary and a conclusion. Jet noise from aircraft remains one of the major source of noise driving aircraft career operations and cause a lot of health problems like hearing damage, even loss. Large-scale turbulent structure within jet turbulence is one component noise source and cause the dominant noise source in the downstream direction. And a lot of researchers are conducted in the effect of large-scale turbulent structures. The Kelvin homoholes instability wave are responsible for the formulation of large-scale turbulent structures, and the noise from instability waves are predicted and validated. In the experiment, we can see this figure quoted on Professor Michel, the circled region in the instability waves. Therefore, our objective is to understand the relation between the upstream and downstream turbulent waves from large-scale turbulent structure with statistical analysis. This is our program structure, which is combined experimental numerical method and the theory part. From our theory, we can have auto solution, and the amplitude can be calibrated with the numerical method, and we can find the pressure time history and sound pressure level. At the same time, the pressure time history can be measured by the experiment, and the sound pressure level can be computed. Then we can do the statistical analysis to analyze the noise source and the relation between different locations. The small perturbation equations that govern the instability wave are derived from the linearized invasive equations of motions in the non-dimensional form as these three equations. The instability wave formula can be expressed as this asymptotic expansion form. We apply the method from Tim and Burton by separating the flow into inner and outer regions. In the inner region, we use the article scale analysis method and combining the instability wave formula to simplify this governing equation into an ordinary differential equations. Then this solution can be expressed as the combination of two linear functions with two unknown amplitude functions. In the outer region, we still can simplify the governing equation with the Fourier transform method and the mean flow field. Then the solution can be expressed as in an integral form with an unknown amplitude. Then we apply the matched asymptotic expansion method to find the relation for these three amplitude functions with these three equations. In sum, the single instability wave solution in the inner and the outer region can be expressed as these two equations. In order to find the far-field noise, it is much easier to transform the cylindrical coordinate to spherical coordinates. Only those noise with supersonic phase speed can radiate as noise. The stationary phase approximation method was applied, and finally the far-field noise can be expressed as this equation. In this program, a bioconic nozzle with a design Mach number 1.76 are designed by Mr. Goldschmidt and Dr. Ukeiley. The nozzle exit diameter is 2 inches. This figure is a solid and fabricated nozzle used for this program. A series of experiments were conducted at the University of Florida and Anechoic Wind Tunnel. The duration time for each experiment is 30 seconds, and the cutoff frequency is 100 Hz. The operating conditions are the jet for jet exit Mach number is 1.3, NPR is 2.77, TTR is 1. Three groups of experiments were conducted. The first one is at hour d equals 30, from 150 degree to 50 degree with 10 degree interval. We call this far field. The second one is at hour d equals 15, from 150 degree to 50 degree. We call this as near field. The third one, we used two microphones simultaneously to analyze the correlation between upstream and downstream. We fixed the microphone at 50 degree at hour d equals 15 and moved the other microphone from 150 degree at 50 to 50 degree at hour d 30. This figure is a comparison of sharing between our LES results and experiments. The upper one is from LES, which is instant flow field, which is conducted by Mr. Shen. This solver is a modified high-files code, which is a compressible Navier stock solver. The lower one is from experiment, which is averaged by 1,000 samples. From this comparison, we can see that a barrel shock is formed as a nozzle exit. The periodical shock cell structures were captured accurately by our numerical method. Based on the LES database, we can predict the far-field noise with Kirchhoff surface method. We believe that outside the surface, the nonlinear and Wigshir's effect can be neglected. Therefore, we can using this wave equation to predict the far-field noise, and we apply the method from Friend by transforming the wave equation in terms of time, stream-wise direction, and azimuth direction. And finally, we can find the exact solution for this wave equation in cylindrical coordinates. Similarly, with the instability wave theory, we can find the far-field noise by transforming the cylindrical to spherical coordinates. The final result is here. Firstly, we verify the far-field noise with chaos method. These three figures are the sound spectral from experiment and the chaos method at one upstream direction 60 degree, sideline direction 90 degree, and downstream direction 140 degree at hour d equals 30. From these figures, we can see that when stroke number larger than 1, the sound pressure level decays rapidly due to the resolution of space and time. At 60 and 90 degrees, there is an over-prediction at lower frequency due to the open shell of KS method and the abruptly increment pressure on the surface. Then we remove this increment, the results are highly improved. Therefore, we believe our numerical method is valid to predict the far-field noise. Next, we show the far-field noise predicted while instability wave models. The amplitude can be calibrated with the chaos method at 140 degree, where the noise source is dominated by large-scale turbulent structures. These three figures are also the sound spectra at similar angles within the stroke number less than 1. So, from the 60 and 90 degree, you can see that at a lower and a higher frequency, the sound pressure level is lower than experiment, which is in physical sense, but at this range, the sound pressure level oscillates. That's due to this method is linear, but in this jet flow, there are nonlinear effects caused by the interaction between the large-scale turbulent structure and the shock-scale structures. Next, we turn to the statistical analysis. Firstly, we show the autocorrelation at 60 degree, 90 degree, and 140 degree at hour d equals 30. The solid black line is from experiments, the dashed line is from our predictions. At 140 degree, you can see that there's a wide and negative peak, which shows that noise source is from large-scale turbulent structures. In the 90 and 60 degree, there's clean ring here, which means the noise source is a combination of fine-scale and broadband shock-associated noise. Our predictions also show a negative and wide peak at 60-90 degree. Next, we show the cross correlation at the far field region. We choose the reference microphone is at 140 degree outward equals 30. The comparison angle is 60 degree, 90 degree, and 150 degree. For the 150 degree, you can see there is a obvious peak, which means that the noise source is similar for these two angles and are also from large-scale turbulent structures. In the 60 and 90 degree, the correlation from experiments are almost non-existent, which means that noise sources are distinctive for these two angles with the reference angle. But for our predictions, the correlation are high, which means that noise sources are similar with the reference angles. This figure is a comparison of maximum cross correlation between predictions and experiments at the near and far field region. We choose the reference microphone at 50 degree outward equals 15, while other angles is at outward equals 13. Firstly, we compute the time lag approximately using this equation, and the source location are chosen at different streamwise direction 0, 2.25, and 4.5 to represent the large-scale turbulent structure locations. From the experiments results, we can see that they are almost overlap, which means that the choice of source location doesn't alert the results. And when the degree less than 100, the correlation almost non-existent, which means that noise sources are very distinctive in the upstream and downstream direction. An alternative way for ascertaining the relation between the radiated noise is by coherence. Therefore, we firstly show the far field coherence. We choose the microphone at outward equals 30 and 140 degree. For the experiment results, you can see that 140 degree and 150 degree has a larger coherence, but for other two angles, the coherence is relatively low. With our predictions, we can see that the coherence varied at the similar range from 0.3 to 1, which means the noise sources are similar. Next, we show the coherence for the near and far field region. We show the reference angle at 50 degree outward equals 15. From the experimental result, you can see that the coherence is low relative to our predictions. And for 50 and 60 degrees, there is a peak around the stroke number 1. This is due to the dominant noise source is a broadband shock-associated noise. And also in our predictions, the coherence varies from 0.3 to 1. This is our summary and conclusions. In this program, we applied the numerical method, experimental measurement, and the theory part. The numerical results show that it is valid to predict the far field noise, and the coherence and correlation between the upstream and downstream direction are nearly non-existent from experiment. But for our predictions, the correlation and the coherence are high. In the future, we will try to extract the noise source from large-scale turbulent structure in the upstream direction and improve the prediction from numerical method at the near field region. That's all. Thank you for your attention.